Well, be very good. Well, okay. Are we ready?
Yeah. You want to? You start us off, then, Andrew.
Okay. Well, welcome everybody. We're very excited to have Greg Beroza from Stanford University here. I bet everybody on this call know Greg, and he's going to talk about deep learning for earthquake monitoring. A lot of exciting work has been coming out of his lab over the past, I don't know how long, Greg, 5 years or actually longer with the
exciting
hash.
stuff goes way decades.
I'm too young for that.
Yeah, I know. Yeah. Well, thanks, Ben. So if it's okay, I'll just go ahead and get started.
Sure.
Yeah. So I'm going to talk about deep learning for earthquake monitoring, and so I'd like to thank Chris and the rest of the group for inviting me to give this talk and for being here the day after Easter to listen. So this is going to be kind of an overview talk. It's going to be sort of technique focused, but at the end I'll show some applications and I'll sort of appeal to the group for maybe trying to develop a wider application of deep learning in earthquake science. So it's just my name on the title slide, but I will try during the talk to give attribution to the appropriate students, postdocs, research scientists, and other colleagues who did the work behind it that I'm going to be showing. All right, so I've got. So first question, can you guys see my cursor?
I don't see it.
No, okay.
I don't, but there's.
All right, so I will describe where I want, when I want to. I won't try to point. I will go ahead and describe things. So, yeah, so here's a schematic of an earthquake monitoring workflow. So on the left these are seismograms, waveforms, records of the ground motion at particular places on the Earth's surface. Here they're arranged by distance, so it's like a record section, but in general, we don't know where an earthquake source comes from. You can see the P wave and the S wave as the two main arrivals in that. And so that's our input, and we're getting this input 24 hours a day, 365 days a year. And from that input, we want to output a earthquake catalog that's shown on the right that is as comprehensive as possible. That is, it has as many events as we can detect given the network that we have. And so this catalog is a set of discrete seismic events with locations, magnitudes, perhaps higher order information like focal mechanisms, stress drops as well. So classically, we divide this workflow into stages. There's pre-processing, which might be filtering or removing bad channels. There's a set of related and sort of entangled processes, detecting an event, picking the phases, which is often how we detect an event, associating those phases to a single event or a set of events, sometimes called phase association. Then once we figured out that we actually have an earthquake, such as the one on the left, locating that earthquake and calculating its magnitude and so on and so forth. And we want to do this as comprehensively as possible. And then in this talk, I'm going to be pushing using machine learning and in particular deep learning for that function. So the first thing I'm going to talk about very briefly is a data set that we assembled for this kind of for training deep neural networks. So important thing to know is that deep learning is data hungry. So these many layered neural networks require a lot of data in order for them to learn the general rules that seismologists use to, say, pick P&S waves or determine an earthquake from noise. Seismology, unlike a lot of fields, is really lucky in that we have very large data sets that have labels on them. They have examples, waveforms with pics of P waves and S waves, maybe even surface waves like the one shown here. Many fields don't have that, and so they have to generate these large sets of labels, and we have a big advantage. However, as all you seismologists out there know, these labels are rife with errors. and if we have mislabeled data, then our neural networks will not learn as effectively as we would like them to. So earthquake catalogs have issues. That's another way of saying that. Sometimes we have a set of waveforms. So this is 3 components of ground motion, vertical and 2 horizontal components, where the catalog says there's an earthquake, but there's apparently no earthquake. Sometimes we have examples where this is actually fairly common, where we have an earthquake that's labeled with the blue and the red bars on the left for the P and the S wave. You can see there's a smaller earthquake near where the arrow is, but that's not labeled. That's not in the catalog. So if we tell our neural network that that little earthquake is not an earthquake, is in fact noise, it will learn exactly the wrong thing. It will learn to ignore little earthquakes, which is the last thing we want it to do. And during rich swarms and rich aftershock sequences, there may be many uncatalogued earthquakes. So this can be a real problem. And then catalogs sometimes, for one or another reason, have bad picks. So if we're training a network to pick P-wave arrival times, for example, using the blue bar as the P-wave onset, it would learn the wrong thing. It would learn to pick it improperly. So Mostafa Mousavi, who used to be at Stanford, he's actually still adjunct at Stanford, now works at Google, but he assembled a global data set of seismic signals for AI. Not a huge data set, 1.2 million seismograms from 500,000 earthquakes from around the world, all at local distances. And he spent a year doing basically quality control, making sure that the earthquakes, and adding labels so that the labels were accurate, making sure that the noise samples were in fact noise and didn't have any earthquakes in them. And then he published this in IEEE Access. That's a journal I'd never heard of, but it's meant for publishing data sets. And in this journal, he did a couple things to help data scientists, that is non-seismologists, use this data. For one, he put it in HDF5 format. That's a data science friendly format with easy IO. And there's also, I mean, you might get a laugh reading it. There's a lot of seismology 101. What is a P wave? What is an S wave? That kind of thing. And the idea is to recruit the expertise from data scientists who are developing new methods and get them interested in the kind of problems that we're working on in seismology. So that's a bit of onboarding for that crowd. And I was really happy to see that published just a few months ago, Magrini et al. Assembled separately a data set with the same sort of goal in mind. Again, for local earthquakes, they have more larger magnitude earthquakes in it. We still have to do this for more regional phases and for teleseismic phases, because apparently there are challenging problems there as well. But it's good to see that others in the field are taking the same kind of efforts. I think that's important. Okay, so we now have a fairly big data set for training neural networks. And so now I'd like to start talking about pieces in this machine, or pieces in this earthquake monitoring workflow, and how we can use deep learning to improve things. So a classic problem in seismology, actually in many fields, is how to separate signal from noise. So on the left, we have an earthquake arriving sort of in the middle of the window. So that's ground motion versus time. But you can see it's riding on strong background noise. That's our typical situation, particularly for small earthquakes where the signal noise ratio is small. And in noisy environments like the ocean floor or islands or cities, we're always dealing with noise. And so what we'd like to be able to do is to separate that signal from the noise. So shown on the right is our idealized outcome, where the upper panel shows the earthquake signal, the lower panel shows everything else, which is the noise. And so what we did in this paper, published a couple of years ago, was to come up with two masks that are complementary. They're arrays of real numbers in time, frequency, space. So frequency is on the vertical, time is on the horizontal. The upper window, so that's number 4. So one shows the sorry, you can't see my cursor. One shows the complex spectrum. So this is the complex spectrum, not the amplitude spectrum. But the middle panels here show the mask. One passes the signal, one passes the noise. And the signal, you can see, has a time frequency behavior where the high frequencies decay quickly, the low frequencies decay slowly. We know earthquakes will behave this way. They're broadband, but they're also attenuated. And the noise has certain characteristics as well. So we apply those masks. We got the panel just before the end, we do an inverse transform and separate the signal from the noise. So that's the idea behind this approach. And the way we develop those masks is with a very deep convolutional neural network, shown schematically here. And so the idea is we actually recombine samples of signal and samples of noise such that we have close to 1 billion combinations. Of the two, we vary the signal level when doing this. And we train this deep neural network to learn that those masks that will pass through the signal and its complement the noise. So we're learning this mask, and then we can apply it to data that were not used in the in the training to see how well it works. And that's what's shown here. So at the top is our clean signal. For the clean signal, it's not pure signal. There's actually some noise in there, but this is a high SNR record of a local earthquake waveform. The second panel shows a sample of noise. This is data from the same instrument where we don't think, at least, there's any earthquake in there. And then the third panel shows there's some. So that's the input to the neural network. The output, after we do the inverse transform, is shown with the bottom two panels. So the second to last panel is the recovered signal. The last one is the recovered noise. And zooming in on the first arrivals, the P wave and the P wave coda are these windows. You can see there are differences in these inset windows. They're not exactly the same, but they're more similar than they would be if we had done something simple like just bandpass filtering, right? So that's the advantage of training it to find the time frequency behavior of signals, is that we can better recover that. The bottom panel shows the recovered noise, and if you look carefully, you can see that is where there's signal between 7 and about 13 or 14 seconds. The amplitude is smaller than it is in the second panel where it's noise. So there's a little bit of crosstalk here between signal and noise, but it's better than it does better at competing approaches. So let me just show you a few examples of this. Here's a clean signal and noise. There's some, and then the recovered signal. Again, you can see the same effect where the recovered noise leaks into the signal. The noise is smaller than the original noise. We can try to trick it by just not having any signal, just giving it a bunch of noise. This is the sort of noise that a STA, LTA phase picker might pick lots of arrivals for. It's smart enough to know that these are not earthquake signals, and so we recover no signal in this case. I could show you lots more of those, but it gets old pretty quickly. An important issue is whether we do better in recovering the things we're interested in. So one of the things we're most interested in is arrival time. So this is an attempt to show how well we recover arrival times. So this is using a known signal, such as I showed earlier. And what's shown is the cross-correlation based arrival time difference between the true signal and the recovered signal. And it's as a function of decreasing signal to noise ratio. So as we go from left to right on this figure, we get weaker and weaker signals, or lower and lower SNR. And where we want to be is at 0. So that means there's no difference between the observed and or the true and the recovered arrival time measurement. And you can see at high SNR, all the different methods do well. The noisy signal is with the blue crosses, and that diverges pretty quickly, starting around 9 dB. If we do normal filtering, shown in green, we do better up to a point. The red crosses are deep denoiser, which faithfully recovers the arrival time until around 2 dB, and then it too gets defeated by the noise, as we expected it would be. We're not doing magic here, but it does, against the denoising techniques that we compared it with, it does a lot better. And I could show you a similar sort of picture for something like amplitude that we might also be interested in. We didn't look at polarity. We haven't really looked much at polarity, but anyway, that's so that's an improvement to pre-processing that we can do using using deep neural networks. So the next thing I'm going to talk about, and I'm just going to talk about this briefly because it's already out of date. It's a year and a half old, and that's an event detection method that we call CRED, and CRED stands for Convolutional Recurrent Earthquake Detector. So the idea here is that we have 3 component seismograms as input. We have their time frequency representation here. We have a series of convolutional layers that learn efficient and effective representations of the spectrum, and then what are called the recurrent layers. These are layers that are meant to capture the sequencing of events within say a time series. So we know from seismology the P wave comes before the S wave, comes before the coda, and these layers are meant to capture that. And then the output is a classification, which is binary, either not earthquake 0 or earthquake 1. And we defined earthquake to be the P wave arrival time plus 3 times the S minus P time. And so shown on the left for 2 panels, 2 examples of noise, showing that it's returning 0. That's the lower green line in each panel. And then the right 2 panels, or sets of panels, show that it recovers the earthquake when the earthquake is occurring. It looks sort of like a step function there, or a Heaviside function, in terms of the classification. So we did similar kinds of tests here. We showed that it works for local earthquakes. Ground truth is shown with the solid line. The dashed line shows the prediction, that is the output of the earthquake detector. Here we have a common case where there's a bad channel for one or another reason, and it's smart enough, just like a seismologist would be, smart enough to focus on the other 2 channels that faithfully record the earthquake and ignore the bad one. And the lower panel shows, even when we have more challenging noise sources, it's smart enough not to detect an earthquake at that time, or it's learned enough not to do that. Okay, very quickly, I'm gonna talk about, really just mention a couple of applications for location and characterization. So the first is for single station earthquake location. So we use the STAD data set, the global data set, to train a neural network to predict 3 things. That is the distance to the earthquake, the P wave travel time, and the back azimuth. And so these can be used. This is sort of a proof of concept paper, really, showing that it's possible to do pretty well at single station earthquake location. What's shown on the bottom is the distribution of the prediction errors. So we have a catalog of course, to predict these locations with the distribution of the P wave travel time and the distribution of the back azimuth. And I have to say that we had to be pretty careful with the stations here, because it's very common for the horizontal components to be inaccurately labeled. So Mustafa put a lot of work into making sure that those labels were accurate before running this test. So if we look at how that manifests for a single station, so here's one in Southeast Asia. This is from a single station to the south east of the true location. And I should say the true location, our ground truth is a little bit squishy here. That's the best estimate of the location based on the catalog, which itself might have errors that are not not necessarily fully captured. So this does acceptably well. The prediction of the location is within the error ellipse of the source. Here we're, for the one on the right in South Africa, we do not perfect, but pretty well in capturing the location with a single station. So who cares? Why would you want to locate an earthquake with a single station when you have a whole seismic network? There are a lot of reasons for wanting to do that. One is that for very small earthquakes or very sparse networks, really this is the main reason, for very small earthquakes or very sparse networks, we may only have one station or a few stations to base a location on. So this is actually quite useful. So that's the location. We've also done a single station magnitude network, so we call it MagNet. And this again is based on a global data set. This shows as a function of the predicted magnitude, or shows the predicted magnitude as a function of the catalog magnitude. Here again, it's a little bit difficult because we didn't have location uncertainties on the measured magnitude, but you can see there's a straight. It depicts a straight line with a slope of very close to 1. On the right side shows the standard deviation of the magnitude, and it's about a few tenths, 1 to 2 tenths of a magnitude unit for most of them, which for a single station is pretty good. That's typically what the magnitude uncertainty is for multiple stations, and presumably, if you had multiple stations to work with, you could reduce that error further. But again, this is kind of a proof of concept paper. It's not. There's plenty of room for improvement in this method.
Yeah, can I ask a quick question?
Of course.
How much is that built on there being events in the catalog very close to the events you're trying to characterize? Or can you do with a sparse catalog?
Yeah, you could. So that's a kind of a deep question. So if, you know, in machine learning, we try to separate what's called the training data set and the validation data set from the test data sets. So the idea is that the data that's withheld provides an unbiased estimate of the performance of the network. Now, in real earthquake catalogs, if you go to a region and you have repeating earthquakes or near repeating earthquakes, if you have repeating earthquakes, you have an earthquake that your neural network might have seen before, essentially, wiggle for wiggle, the same. And so presumably it should work just about perfectly in recovering the magnitude. And because that data is essentially not independent, you're not getting a good test of the performance of the neural network. It's not an unbiased. There's a bias built in through the correlations of the data. So I don't have it for this one, but for other, so a better test is to test what's called generalization. That is the ability of a neural network to learn how to interpret data it hasn't seen, is to use data that's like from a different region. So I'll show you in a little bit an example of data from Japan, which we couldn't include instead because of their data redistribution policies, where we do a good job at recovering, not magnitude, but detecting earthquakes and measuring P&S wave arrival times. But yeah, it's a interesting question. On the other hand, you know, if you have in your catalog an exact match waveform, maybe you don't care. You know, if you're just concerned with earthquake monitoring in Southern California and you can identify very quickly that an earthquake is a repeat, you know, in a sense, you're done, or you can get a very accurate magnitude, and you don't care about whether it works on an earthquake in South Africa or something. So, of course, like everything, it depends on what you're interested in. Okay, so now I'm going to talk about phase picking using a convolutional neural network that we call PhaseNet. And so here, and I'm not doing this in chronological order. This is one of the first things we did because it's one of the most useful things to do. So here, this is before we developed that data set. So here we use a data set from Northern California, a bunch of P and S wave picks, about 500,000 of them, I think we used in this case. So the input is 3 components of ground motion, and the output we engineer to give us what we want. So the output is a classification of the continuous time series as either a P wave, an S wave, or neither. That is noise. And the way Wei Chung trained this is he took a truncated Gaussian with 0.2 of a second width with the peak at the P wave arrival time and at the S wave arrival time. And so the idea is we want this neural network to not just identify the P wave and the S wave, but to have that probability peak at the P wave arrival time and at the S wave arrival time. We did it pretty naively. We didn't account for the fact that P waves and S waves aren't picked as accurately as one another. We didn't take into account the quality in the catalog. We just did it assuming all the picks were the same. We also didn't do the extensive quality control that Mustafa did for the STED catalog. So the fact that it works means that the Northern California seismic network picks, by and large, are pretty good. So the total data set was 750,000. We held some of that out for validation and some for testing. I forget exactly how many we used in the training, but here's the output. We have time increasing from left to right. We have a P wave pick and then an S wave pick and the top 2. So the top 2 panels are sort of easy cases. We're at high signal to noise ratio. The middle panel is an example of strongly clipped data. So there's a lot of strongly clipped data in the data set, in the data center. And seismologists have learned to, say, pick the P wave based on the, the S wave based on the change in frequency content. And so the neural network learns to do that as well. So it works pretty well on clip data. We didn't denoise here or even filter. And so it's learned on this unfiltered data to pick P waves and S waves. And importantly, it picks them separately. It classifies them separately. And many phase association algorithms assume you don't know whether it's a P wave or an S wave. For the association part, that's some new information, extra information that we can use to do a better job. So again, we can compare it with ground truth, in this case provided by analysts. So a histogram of P waves and S waves from PhaseNet on the top versus a standard approach. I think this is the AR picker in OBSPI. Anyway, what you see is that both methods do pretty well for P waves. There's a little bit of skew towards late arrivals with the standard approach that's absent from PhaseNet, or at least very subtle in PhaseNet. It's in the S wave, which are hard to pick, that the neural network really moves the bar. And you probably can't see it, but the peak of this S wave distribution is 14,000 for PhaseNet, whereas it's 1,400 for the standard approach. There's a lot more dispersion in the S wave picks, and there's a very noticeable late skewing in arrival time measurements. Okay, so just wanted to say a little bit about, so we said the deep learning is data hungry. And so it's important to have large data sets, but we have a situation in seismology that for some problems we're really very interested in, we don't have large training data sets. So we have to be inventive, and data augmentation is a technique that data scientists use to sort of artificially inflate the amount of data we have to work with. So examples in seismology, fortunately, we don't have very many large earthquakes. Fortunately, there are a limited number of nuclear tests. So, you know, these are examples of things we're interested in for which we lack large data sets. So the idea behind augmentation is that we generate new, and that new is in quotes because it's not really new, but we generate new training samples based on the data that we have and our understanding of that data. And the idea is to make the deep learning methods work better than they otherwise would. So I'll try to show this schematically.
Hey, Greg.
Yeah. Yes.
Yes. When you talk about numbers in that context, does a 3-component seismogram count as 3? Three different.
I would.
Is it?
I would say no.
I see.
That's what. I mean, I like to think of. Depends on who you talk to. So, but that's. I mean, it really helps. For example, for phase picking, we can pick S waves with just the vertical component, but it's a whole lot easier. It works much better. Not surprisingly, if you have all 3 components.
So you're picking them all together. You don't pick them separately. I see. That's why you think of it just as one.
If we have all 3, we do them all together. If we only have one to work with, then we work with one.
Gotcha.
Yeah, and I should say that I'm not going to talk about distributed acoustic sensing, but pretty soon seismology is going to be absolutely flooded with lots and lots of measurements, not of vector motion, but of a component of a tensor, and which has stronger angular dependencies and so on and so forth. And so I'm sure that machine learning approaches are going to be important for learning how to extract, how to do earthquake monitoring in that context as well. Okay, so let me just because I think it's important, talk a little bit about data augmentation. So here's an example where we're trying to tell the difference between negative training data, so that might be absence of an earthquake or noise, versus positive training data. So that might be the presence of an earthquake, or maybe it's a P wave arrival, depending on what we're training it for. So the true boundary between these in this hypothetical construct is a linear combination, as I've drawn it, between feature Y and feature X. And so the idea is the neural network learns feature Y and feature X by seeing lots and lots of examples, and it figures out where, and you want it to figure out where the true boundary is, such that you don't get any false positives. So false positives would be when you this is the learned boundary shown in green. False positives are when you think you have something, say an earthquake, but you really don't. It's noise. So false positives are bad. Their complement, false negatives, are when you think you don't have an earthquake, but you actually do. So depending on the context, false positives and false negatives, there's a bigger penalty for one or the other, but really we'd like to suppress both of them. And so the way we can do that with data augmentation is to effectively expand each of these data sets such that the learned boundary gets closer to the true boundary and we make fewer mistakes. And so conceptually, I hope that's helpful. That's the idea behind getting larger data sets or augmenting the data. And of course, there'd be no point in doing this if there were only 2 dimensions. We have many high dimensions, and so learning these boundaries is a non-trivial exercise. Okay, so let me show you a trivial example of that. So suppose we trained our in training our neural network, we aligned the seismogram such that the P wave arrives exactly at 10 seconds within the window. Then we train, and let's say we have 500,000 examples of this. We train the neural network. If we do that, the neural network will learn the wrong thing. It will learn that we align the P waves at 10 seconds. It'll ignore the waveforms, and it will always pick the arrival time at 10 seconds. So here's an example where we have a 30-second window of a seismogram. The P wave is near 25 seconds, the S wave at about 29 seconds. The blue dashed line, if you can see colors on your screen, is if we train it poorly, it picks it at 10 seconds anyway. So that's a badly trained neural network. If we shift the arrival time around by 10 to 15 seconds, That's what's shown in orange, and it gets the P wave because it's just within 15 seconds. It doesn't get the S wave. But if we shift it everywhere within the window, then it gets a very nice P wave, and it does okay at the S wave, which is mostly cut off from the window in this example. We'd want to be doing a running window anyway. But this is an example of if you trained a neural network poorly, then you can get the wrong answer. And so this is a trivial example of data augmentation, just moving the seismogram around in the window. It's not new data, but it's data that's presented in a slightly different way, and it allows the neural network to learn properly how to pick P waves. So here's a somewhat less trivial example. And here we have three components of motion. If we train a neural network with only one P wave in a time window, then it will learn to only pick one P wave in a time window, even when there are two or perhaps more. And earthquakes, as you know, cluster in space and time. So this is not something we would want it to learn. So that this 1, 2, 3, fourth window down shows the output of a poorly trained neural network where we only allow one P wave and one S wave per window, and you can see it peaks. One peaks at the P wave, one peaks at the S wave, and it completely ignores that second earthquake that comes in at about 15 seconds. The lowermost window shows a neural network that's trained to have seen multiple earthquakes within a window, and so it's smart enough to be able to do that properly. So that's a less trivial example of data augmentation. This is a real pair of earthquakes, but you could easily imagine superposing a whole bunch of earthquakes on top of one another and training it to fly in the challenging problem of, say, early aftershock sequences. Okay, so that was PhaseNet with a side for augmentation. Mustafa Mosavi is going to talk to you in 3 weeks about earthquake transformer and some other things. I just wanted to mention it because it combines event detection and phase picking. And I think that's a trend that sort of hybridization or combination is a trend that's going to continue. Earthquake transformer, it's like PhaseNet. There's 3 component data as input. Unlike PhaseNet, it's not purely convolutional. There are recurrent layers that learn the sequencing. There's something called attention mechanisms that learn to focus on the most important parts of the seismogram. And there's also multiple outputs. So it's got one set of encodings and multiple decodings to give you light cred. The left one shows the earthquake signal or not. Like PhaseNet, the middle one shows where the P wave is, and the one on the right at the very bottom shows where the S wave is. Now, knowing that there's an earthquake, knowing that there's a P wave, knowing that an S wave comes after that, that context is how seismologists read seismograms. It's not how PhaseNet works. So PhaseNet just looks at a seismogram and says, is that a P wave? 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 It's not smart in that sense. Whereas earthquake transformer says, here's an earthquake waveform. There's a P wave at the start and there's an S wave somewhere later. It does all of those at once, and as a result, it works better. So this just shows the example of the earthquake transformer output. The green bar shows where the earthquake signal is, and then the P wave pick and the S wave pick within it, just like PhaseNet. And for now, at least, and this is going to change within a year if it hasn't already, it outperforms conventional approaches and other machine learning based approaches. So this is the same kind of histogram for P waves and for S waves of earthquake transformer versus the second one down is PhaseNet, generalized phase detection, use, PPKNet, PICNet. There's lots of new models being published monthly now. And so, but for our application, our demonstration, our test data set, it outperformed the other methods. And that test data set, this is getting back to John's question, came from Japan. This is data that was not trained on at all. And well, so Mustafa will talk more about this, but the panels, the two panels on the right show the subset of the stations we use for detection and location compared to a very careful study carried out by the Japanese that used about 3 times as many stations. We were able to get 2.5 times as many earthquakes, including some earthquakes that don't show up here under a volcano that were not in the Japanese earthquake catalog. I apologize for the dots being too small, but Mustafa will talk about this in 3 weeks and explain in greater detail how attention mechanisms work and well, presumably other things. We'll see. Okay, so let me just talk about a few applications. So this is paper published last year, the Guy Greenbrier, Arkansas earthquake. We developed a complete machine learning based catalog for about a year's worth of data. We trained PhaseNet on the Northern California seismic network data and we did not retrain it for this study. So this is another demonstration that PhaseNet in this case generalizes well. We were able to get precise locations for 90,000 events. We detected some large multiple of that number of events, but there's so few instruments in this part of the world that we weren't able to locate them precisely. Anyway, the sequence illuminated this fault that cuts through the map that's shown in gray. That's outlined with seismicity. And the gray ones are the events that are occurring along what's called the Guy Greenbrier fault now. And it's thought that these things in hexagons, 1 and 5, these are deep disposal wells that are injecting mostly produced water into the formation right above basement. And these were implicated in triggering the earthquakes. In particular, well 1 and well 5 were shut down after a magnitude 4.6 earthquake occurred near the southern end of this distribution. The colored events are ones that are off that fault, also within our catalog. These we think are primarily due to hydraulic simulation or fracking. So this sequence has been studied by multiple investigators, including us, but this machine learning based catalog that we generated nevertheless gave us some new and fairly important insights into the sequence. So here are the two wells with the red, well 1 and well 5. Notice there's also a well 2 in the lower left part of the figure. What's shown on the right is a space-time diagram of the earthquakes in our that we were able to detect, and these are just the earthquakes that are in gray on the one on the left. So they're ones along the fault. Also shown are the locations of well 1 and the time when well 1 and well 2 started and when it stopped. And time is shown at the bottom. This is calendar time. It's about a year's worth of data. So what you can see is that the earthquake sequence starts up near somewhere between well 1, maybe near well 1 and well 5. And in October 2010 is when it really gets going. And it spreads over a large part of the fault, sort of spanning from well 5 to a little bit north of well 1. But the February sequence, which included the largest one in the sequence, shown with a star, which caused them to shut in well 1 and well 5, actually starts separately. So that the sequence is really like two sequences. It's multiply connected, and it ruptures back towards where the first sequence was. So it's not clear to me that shutting well 1 and well 5 off was necessary. It could well be that well 2 is the well that triggered the sequence that caused the larger earthquakes. So despite the fact that this sequence had been studied by multiple investigators, this character of the sequence, which is important to figure out what's going on, was not identified until this paper. The other thing you notice is because we have so many earthquake detections, you see these little these parabolic shapes that reoccur over. So we're looking in space and in time, parabolic shapes that recur over multiple scales, including, this is where the cursor would come in handy, but including the whole sequence on the right, the second sequence, as well as the little arc-shaped structures that are smaller in extent and in duration. Those are characteristic of diffusive processes, and if we sort of simple-mindedly calculate a diffusivity, we get very big numbers, something in the range of 1 to 100 meters squared per second, most of them around 10 meters squared per second. This is much higher than we would expect for diffusivity in the bulk, and it probably means that the diffusivity is fracture control. But it's useful information for people who are modeling this sort of thing and trying to figure out the hazard from induced earthquakes. Margarita's on the call. She's going to talk about this, I hope, in sometime in May. But we applied PhaseNet to the Amatrice Vizo Norcia sequence. The INGV catalog is a very rich sequence on a cascading earthquake sequence on a set of normal faults. 82,000 events over a 1-year time period. That's one every 6 minutes. We ran PhaseNet on the continuous data, 28 million PPICs, 31 million SPICs. So, this is weird for seismologists. We have more SPICs than PPICs. The reason is that PhaseNet does very well on S, and S waves are bigger than P waves. So if you've got a picker, if you got a small earthquake, you can pick the S wave, but maybe not the P wave. Anyway, the PhaseNet catalog, the whole catalog has well over 1 million events. 900,000 of them, we have enough picks to locate them accurately. That's one every 35 seconds or so for a year. And this is so the top shows the INGV catalog. The one on the bottom is the PhaseNet catalog. And we're using this to try to improve methods of earthquake forecasting, such as looking at secondary triggering and spatial variations in the orientation of receiver faults that we can recover given these more precise locations and more complete earthquake monitoring. Whoops. Shifting back to the US, this is for Oklahoma and Kansas. So this is for basically a decade worth of data. So I should have there's a map up here that shows the state of Oklahoma, state of Kansas. Doesn't mean anything to those of you in Italy. Anyway, this is the middle of the US, and it's a place where we've been having a lot of induced earthquakes. And these are earthquakes color-coded with time, with the blue being 2011, the brick red being 2020, and the warmer colors being the more recent earthquakes. It's hard to see anything here, so I'm going to zoom in on this area in the red box that includes the Pawnee earthquake. That was one of the 4 magnitude 5 earthquakes that happened in Oklahoma during this time period. This is what we see. So this part of the state, and actually parts to the left as well, and into southern Kansas, are actually riven with small alignments of small earthquakes that we've been able to detect with this machine learning based method applied over a decade worth of data. And you can see these structures are, well, you can't see how long they are, but this from left to right, this is like 50 kilometers. So some of these structures are 10 kilometers long, big enough to host magnitude 6 sized earthquakes, and yet they're only having smaller earthquakes on them. So that's an interesting question we hope to get at, try to inform with these improved locations. Also, you can see they're very systematic behaviors in the trends of these earthquakes that are presumably reflecting the favorable orientation with respect to the stress field. These results are less than a week old, so we don't have much interpretation of them yet. So here we're back to we're off to the left. You can see the Pawnee sequence just to the right of the triangle. We're going to zoom in to this part here. So the previous high resolution catalog for this part of Oklahoma was a template matching catalog developed by Rob Skumal and his colleagues. It's a bit of an apples to oranges comparison because we have more data, we have a longer time period, although most of it overlaps time period that they have as well. And we're using a different method with a different detection threshold. So it's not really a fair comparison for all those reasons, but we do, what I'm about to show you shows that there is now a lot more information available that can help with the interpretation of these sorts of trends in terms of, say, the stress field, in terms of the evolution with time, whether the largest earthquake occurs early or late in the sequence. These are all questions that we're interested in for these individual fault segments because they're important to decision making and of course earthquake physics as well. Okay, so those are the results I'm going to show. I'm just going to now highlight some work in progress, and we'll end with that. So every time I give this talk, or just about every time I give this talk, I'm asked by regional network operators, well, what about PN and SN? So these are refracted phases, travel through the upper mantle. They're harder to pick than the direct PNS waves traveling through the crust. And so Albert Aguilar, who's a grad student at Stanford, he's working on assembling a much larger supplemented data set that includes lots of PN and lots of SN, such that we can do a better job on picking those phases and improve earthquake monitoring to greater distances. We tried our deep denoiser on the Long Beach nodal array data set to try to see if we could see through the noise and see more events. It basically failed. And the reason it failed is that it was trained on rural noise, that is noise in where Northern California seismic network stations were operating. So we retrained it on the Long Beach data so it would understand and see through urban noise of the type that's seen there. So we used a combination of data from the Long Beach nodal array and the San Jacinto nodal array, where we had lots of sources. And this shows at the left a subset of the traces, about a third of them in the network. Shown on the right-hand panels, B and C. C is just a zoom in of B, shows a denoised record for a small micro earthquake. So this suggests we can see, even in urban environments, we can get rid of a lot of the noise. For the most of the time, we don't have these dense networks, but there's no reason, I see no reason at least, why we can't apply denoising to stations in urban areas like Los Angeles, like Tokyo, that are earthquake threatened, and by doing so, get a better idea of the geometry of faults in those places. You may have noticed that I had arrows pointing to all of these boxes except for association. We're working on 3 different association methods right now. Ian McBrearty is, who I think talked to you guys last year. He's working on a graph convolutional neural network to do association. Weichang Zhu, the guy who wrote PhaseNet, is using a Gaussian mixture model. And Yongsoo Park, who did the work on Oklahoma, is using a hypo-DD relocatable, which is a criteria, which is basically that pairs of arrival times are consistent across the network in order to do the association problem. So all of these are meant to work with machine learning output and when we have multiple events occurring in rapid succession. Lise Retelou, who's now in La Reunion, has worked to get PhaseNet in Earthworm, and they're using it for volcano monitoring in Mayotte right now. And there are plans to install it at Martinique Observatory. They're finding more long period events, more earthquakes in general, even when they're working with OBS data that it was not trained on. And Jean-Marie Sorel is going to be presenting on this at the EGU meeting in a month or two. Weichang Zhu, busy guy. He's also come up with a complete cloud-based machine learning workflow for earthquake monitoring that will be presented towards the end of his talk at the SSA meeting. So the idea is that you have earthquake data, you get it into the cloud, You use cloud processing to pick the phases, to do the association, and presumably to do the location. These guys did this so there's an electrical engineering student and a computer science student involved in this. They did it for a class, and so they sent the output to Twitter. I mean, that's not what we maybe want to do, but the proof of concept is that we can do this and we can do it in real time, and it's scalable. So you add more processors, and they demonstrated that the more processors you add, there's sort of a linear increase in the effectiveness of the approach. So it's a different way of doing it. Importantly, they've set it up so you can swap in modules. So if you don't like the Gaussian mixture model associator, you just swap in something else and make it compatible with this workflow, and you can run the same data through it. So this should really help accelerate progress in earthquake monitoring. So I'd like to close by saying that seismology, I think, is entering a new era. We have these very large networks, so-called large N. We're getting to have a lot of continuous data, decades now of continuous 100 sample per second data. So I mentioned earlier, DAS, distributed acoustic sensing, is going to enable seismology at very densely with challenging measurements, but in interesting areas and with great density. There's also smartphones that can be used for recording earthquake signals. And I would also say that we're not, current practice is not ready for some of these challenges. We treat, current practice using something like STA, LTA, we treat stations in isolation. We don't learn from all the work that's been done in the past to pick phases. And so deep learning can allow you to do that. We also tend to separate the detection, the picking, the association, and so forth without the waveform or the network context that can help us make more reliable decisions. I would argue that earthquake monitoring with AI is ready to go. We have machine learning components for all the pieces. We can concatenate them together into workflows, and it's getting to the point where there's second generation models that are doing better and better. And you should expect that to continue. I think within a decade, we're going to be using the entire network as a sensor, sort of like we use our eyes. We're going to be having hybrids and maybe all-in-one hybrids of these different, now sort of separate modules. And ultimately, this is kind of the easy stuff. The really fun stuff is going to be when we use AI to extract meaning from the catalogs, from the results. So I'm just going to put this last one up here. This is from a paper that Carrie-Ann Bergen published a couple of years ago, suggesting some things that we might do with the big hexagons, sort of bulleted items with the small hexagons, to help accelerate progress in, and not just in seismology, but in earthquake science and solid earth science more generally, using AI. So with that, I'll thank you for your attention and take any questions you might have.
Awesome. Thank you, Greg. Everyone, please unmute. Let's thank Greg together. Greg, lots and lots of things that I'm sure that we're going to hear questions about, but really appreciate you taking the time so early in the morning for you. We would like to encourage questions by early career people, but everyone just raise your hand, and I'll keep track of the order of people raising their hand. And why don't we just go with Paul Johnson to start? Thank you.
Hey, Greg, thanks so much. The work that really recent work in Oklahoma is the patterns you're seeing, spatial temporal patterns you're seeing are just spectacular. We're going to learn a lot from what you've got there. That's just so exciting. That was just a comment, but back to the deep denoiser. when you're doing the masking, you're seeing leakage from the noise training signals and from the data signals, and I'm just wondering if you have any more comments on how you might avoid that.
Yeah, so I agree with you about Oklahoma, first of all, and thanks for that. As far as the leakage between signal and noise, at some point, at some level, it's inevitable because you have they strongly overlap in frequency, and so you're never going to separate them entirely. What we did was, it was kind of involved, but it was really pretty simple. So we just had a bunch of an array of real numbers that either passes or doesn't pass data through as signal or noise. What we could have done, or could do, or someone else might do, is have those be arrays of complex numbers that operate on the spectrum, and that might make better use of the phase information than we do currently. That would, if I were to try to improve it, that would be the first thing I'd try to do. I have no idea if it'll work, but anyway, I'm not sure if that answers your question. I don't, because the frequencies and times of the noise and the signal overlap. I think it's going to be very difficult to do it unless you had unless maybe you could do some kind of matched filter processing, where if you had the noise before and the noise after, you could try to predict the noise during. That would be another way to approach the whole problem.
Yeah. When you do the masking, presumably you're moving it through spectral space, right, and running the model each time, and that's the procedure. So, yeah, I just wondered if you had any ideas, because I'm not sure how you get around it. I don't have any better ideas. It was a question for you, really.
Well, I have ideas, but I have no idea whether they're going to work.
Yeah, yeah. Okay.
There's that. Yeah.
All right. Well, thanks, Greg. Great talk.
Sure. Thanks.
Francesco, and then John Vidali and other people, please raise your hand.
Yeah. First of all, hi, Greg. Thank you for a very nice presentation. I have a question regarding data augmentation techniques, because I'm very interested in this specific field. When you talk about data augmentation, are you also trying to using generative adversarial networks, something like this, or some specific some other specific technique?
So we haven't done anything that sophisticated. So generative adversarial networks, or GANs, are basically sort of dueling networks, where one network tries to trick the other network into misclassifying, say, a signal, and the first network gets better as a result of that. We have just directly manipulated the data